All right. Good morning. Welcome. Let's begin. So today we're going to continue talking about hydrostatic forces on flat surfaces. And as a part of that, I've got a pair of in-class exercises that I'm going to hand out and have you work on together with your classmates. Before we do that, though, I'm going to give you a couple of hints on a pair of the homework assignments just to stimulate your thinking on that. A reminder that homework assignment 3B is due on Tuesday, and as usual you're just going to upload the PDF file of that before class, which is when the availability of it will end. Regarding the lab, I had the suggestion from a student that it would be useful to have an example report from maybe a past semester, and so I contacted the student who I think writes really nice lab reports last year, and he is sending me one of the reports that he did along with his calculations, and so I'll post that sample within the next day or two just so it's available as a resource to you. Along those same lines for the lab, on the first day of class when I handed out the syllabus, I explained the importance of working on your calculations independently, and it's okay to check your solutions with your classmates, but I think that everyone should submit their own work, not submit like group calculations, and that holds true both for our class and also for what you do in the lab. So although you're going to be gathering the data as a group, you're not going to submit a group report, and the calculations should be your own. So I think it's perfectly fine for you to double check your answers to make sure that the people who are in your group got the same ultimate calculations that you did, but you should be able to do those calculations on your own, and they should be your own calculations. Anything you submit with your name on it should be your work. All right. So with that said, any questions related to the announcements before we talk about a few of these homework problems? All right. So last time we talked about hydrostatic forces on flat surfaces, and we made a lot of progress. You had never heard of YCP before class last time, and now that seems like old news to you. So on this one, it's asking you to find the forces of the gate on the block. So let's just briefly take a look at what's going on here, the physical system, before we dive into the formulas and the hydrostatics of it. So there's a gate holding back the water, and the gate is pinned in the middle so that it would naturally pin about that pivot point. And it looks like there's some sort of a concrete that the gate is in contact with, and we can see that the dimensions are showing the depth to that pivot point, and the size of the gate is 4 meters by 4 meters, meaning that it's 4 meters tall, 4 meters wide. And then there's a block at the bottom edge that's holding it so that the gate doesn't pivot. Now, why would it pivot? And think about, if the block wasn't there, what direction would you expect that gate to rotate? Okay, so let's see. It would tip, so if there was a hydrostatic force there, it would start to tip like this. So the top end would go counterclockwise. The bottom end would also go counterclockwise, I guess. So why would it begin to pivot counterclockwise? Good. So he said the pressure acting on the bottom half is higher than the pressure acting on the top half. And the reason for that is that we know that the magnitude of the force is calculated by finding the pressure at the centroid, but the location of the force is at the center of pressure. And the center pressure is always going to be below the center of area. It's just how far below depends on how deeply submerged it is. So the steps here, the procedure you're going to need to follow. First of all, find the magnitude of the force. And so the magnitude of the force, just reviewing the formulas here, it's the pressure at the centroid. That's what P bar means. The pressure at the centroid, the center of area for the gate. And the way that you calculate that is it's the depth of the centroid multiplied by the unit weight. And here it looks like they've said the fluid is water. They didn't say what temperature, so we just use the standard unit weight of water. And the area moment of inertia for a rectangular gate, that's easy enough to look up. And now the next thing you'll need to do after finding the magnitude of the hydrostatic force is the location. And the location of the force, you're going to have to start finding the y bar. Anybody refresh our memory on the definition for what y bar is? Like in words, what's the definition of y bar? Now here it'll be the vertical distance, but more generally it should be the inclined distance from the surface to the centroid. So in this example, delta H is going to equal y bar because the surface we're interested in is vertically oriented. But if it was tipped, then what we'd do is we'd follow the angle of that surface up to the water level, or where the water would be. So the final thing you're going to have to do then is a sum of the moments. So this is kind of a zoomed in view of the gate, and the block is pushing it so that it would rotate clockwise. The hydrostatic force would cause that gate to rotate counterclockwise, and you're going to be left finding the distances involved. Last time in class, I suggested that sometimes this formula for YCP can be more usefully rearranged to say YCP minus y bar is equal to I divided by y bar A. And that the usefulness of rearranging it that way is that then that distance is from the centroid to the location of where the force is applied. So here, rather than finding the YCP, which is the distance from the water surface to where the force is located, why not just find in one step the distance from your center of area to where the force is located? Just a suggestion. Either way will ultimately get you the right answer. Any questions? All right. So here's the other one I wanted to give you a little bit of a head start on. This question is asking the force needed to begin opening the gate. So you're pulling up with the force P, and that's a vertical force, so it's coming straight up. And the water, of course, is pressing on the gate below the centroid and in a direction that's normal to the gate's surface. And so first of all, we have to kind of look at the dimensions here. It's 4 meters is this vertical component. 3 meters is a distance from the edge of the hinge to where the force is located, the P that's being applied. But the physical height of the gate, what's the physical height of the gate? 5 meters, clearly. All right. The hydrostatic force that's acting on the gate is going to be below the center of area, but you're going to have to calculate that using the YCP. And here, since it's inclined, y bar is not going to be equal to delta H. So here's the hydrostatic force magnitude, where you'd calculate the magnitude is based on the centroid, but it's actually applied below the center of area. So you're going to calculate this YCP, and it goes up to where the water surface would be if we extended the water surface. And here you're going to have to do a sum of the moments about the hinge, where P is acting straight up, so the moment distance will be 3 meters. And then this water, the hydrostatic force, you're going to need to calculate the distance to the hinge. But the YCP that you would have calculated is the inclined distance all the way to the water surface. So you'll need to subtract out, let's see, do I have it mentioned here? You're going to have to subtract out this segment length, because that's not included in the moment distance that you'll do as a final step to find P. So YCP is one thing, but then the moment distance is something different. Any questions for that? All right. So I have an in-class exercise that I'm going to hand out. I'd like you to get some hands-on practice on a more detailed level. And for this one, the first problem is a circular plate. We haven't dealt with that yet. We've only had these rectangular plates. So the circular plate has a different area moment of inertia. I'll bring up the formula for that. No, actually, we did an elliptical plate, right? Okay, so we've done rectangular, elliptical. Now we're going to do circular. On the back side, it's rectangular again, but it's inclined in kind of a strange way. So I want to see if you can overcome the unusual orientation of that gate and still apply the process step by step and head in the right direction. So we'll have about, I think, 20 minutes, 25 minutes that we can work together on these, and then we'll be able to go over the solution. If you want to check your depth of the centroid, I've got that value up on the screen now, the delta H. Okay, so on the first one, let's make sure we are all on the same page. Anybody else get 7.10 for the delta H? Okay, good. See plenty of hands for that. Now, the magnitude of the force is simply going to be the pressure at the centroid multiplied by the area. So we have to find the depth of the centroid, multiply that by the unit weight to get the pressure at the centroid, and then multiply by the area. This one happens to be 6.00 square meters. It's almost like that size was selected to give you an area of 6. All right, coincidentally. So the force is 418 kilonewtons. Again, I saw that a few times as I was circulating around. Area moment of inertia, pi r to the 4th divided by 4, so we get the area moment of inertia. And now, on port 4 where it says the location of the hydrostatic force, the way to interpret that is it just means what's the YCP. You know, somehow identify where the force is applied, and in this case we can say the inclined distance from the water surface down to the centroid. So YCP 8.936 meters. Who got that? Great, and you guys are doing great. So the whole point that we're doing this on a handout that you can take home with you, I hope, is that it's going to serve as a template or a reminder on how to do some of these other problems. All right, so we still have a few minutes to solve up the second one. I'll pause again so that you can continue working on that. I put the first couple of answers to the second problem up on the screen there. The depth of the centroid, the pressure at the centroid. Okay, so I got a good question just now as I was walking around. Someone was saying, all right, so for the triangle that takes you down to the centroid of the gate, finding the depth of the centroid, there's the 3 meters, which is the vertical component, and then that takes us from the surface to A vertically. Now we have to go down to the centroid from A. And so there was a little uncertainty on whether the vertical component would be the distance from A vertically to the centroid, or whether we would then need to make another triangle out of it at an angle that's perpendicular to the gate. But remember, it's just the vertical component of this distance that we're interested in, and so it would be the distance vertically from A to the centroid, which is going to be, as it shows here, 3 divided by the cosine of 30 gets us that distance, but it's just 3 times the cosine of 30 that gets us the vertical component from A to the centroid. So it's actually going to be less than 3. the overall physical distance is 3, but the vertical component of that physical distance is less than 3. So sometimes you have to double check what the numbers give you just to make sure it makes physical sense. So here it should be about 5.6 meters is the delta H, which we use to get the pressure at the centroid. And then the magnitude of the force. Any questions so far for what's on the screen? Magnitude of the force, the inclined distance to the centroid. All right, and then the reason why I've done the distance between the centroid and the center of pressure is that that is going to be more useful for finding the sum of the moments than if we go all the way back up to the surface. So let me show it in these terms. So we found this 0.464, which is the distance from, I've got that gap distance indicated on this little secondary drawing here. So it's the distance from the center of the gate to where the force is applied. So the overall moment distance is going to be the 3 meters that gets you to the centroid plus that gap distance. So the moment distance is 3 plus the difference between YCP and Y bar. And then that's counterbalanced in the clockwise direction by 6 meter moment distance and whatever force that the block is applying to the gate. All right, now it's good to be able to work these quickly in an exam type situation, but you don't get awards for working quickly when you graduate and you start at an employer. In fact, I was really surprised. The first job I had, it was a design position, and I thought I'd be doing calculations all day long, but I probably was actually crunching the numbers about 5% of the time and writing the other 95% of the time. Documenting your calculations and communicating with the client. And so you should never feel bad if you're working through these examples at a slower speed as everybody around you. That doesn't really necessarily translate into a bad thing once you graduate. If you're methodical and you make detailed solutions and your answers end up being correct, then that's really what's going to count at the end of the day. All right, so any questions on this in-class exercise before we move on? Anything you want to see, a few moments you need to copy it down again? All right. So with that in the rear view, let's move on to the logical conclusion of these gates which keep turning over. All right, so in the example from last class period, we had a gate that was first vertically oriented, and then it was at a slant, and now what I'm showing is, what if it was horizontally oriented? What would be the forces acting on the gate if it was horizontal? And this is going to transition us into some of the ideas we need to solve forces on curved surfaces, which will be the lecture topic for Tuesday. So we've got a gate that's 2 by 3, as is shown in the dimensions here. It's flat in the water, and we want to find out what are the hydrostatic forces that are acting from above. So we can follow the same process that we have before. You find the location of the centroid, the depth of the centroid, the magnitude of the hydrostatic force by pressure at the centroid multiplied by area, and then the location of the force. In this case, you'd find the location of the force kind of just by inspection. And it's going to be in the middle of, the equivalent force would be in the middle of that plate. And so if the plate is 2 by 3, then it would be 1 meter from this edge and 1.5 meters from the other edge when we look at it from the side view. Okay, so let's do that. Just briefly, and if you've got a piece of scratch paper there or in your notes, follow the process of step 1, identify the centroid and the depth of the centroid. So step 1, delta H equals what? Step 2 is where you find the pressure at the centroid, so that is delta H times gamma. Step 3, the magnitude of the force is the pressure at the centroid multiplied by the area. Okay, let me give you a few moments to calculate that magnitude of the force. That's what we're doing here in the first part of it, and then we'll move on and do the weight of the water. All right, so if we find this just according to the hydrostatic force approach, the force is the pressure at the centroid multiplied by the area. So the depth of the centroid here is 5 meters. That's just the depth from the water surface to the top edge of the plate. So 5 meters is the delta H. We're using the traditional unit weight of water, so 9810, and then the area of the plate, 6 square meters. That tells us that the force from above is 294, 300 newtons. Now, the second thing it asks us here is find the weight of the water above the plate. So the weight is going to be the volume of water above the plate multiplied by the unit weight. And so the volume is going to be an element of water that's box-shaped. It's going to have a front width of 2 meters, a side depth of 3 meters, and then it's going to have a height, this imaginary rectangular box, of 5 meters. So there's some volume of water that's above this, and it just so happens, not coincidentally, that the weight of the water above the plate is equal to that hydrostatic force that we calculated by finding the pressure at a depth and multiplying it by the area. So the two are equal. And there's an important conclusion to be drawn from this. The conclusion that you should keep in mind as we move forward into the curved surfaces is that vertical hydrostatic forces can be computed by finding the weight of the water above the surface. So that's important because when we have a curved gate, the procedure I'm going to teach you on Tuesday is you find out what's the weight of the water above the curved gate. And then that will tell you the vertical forces. And we're going to have to break these problems down into two pieces. There will be the vertical forces and the hydrostatic forces, but the vertical forces are just as easy as finding out a volume of water above the surface. So to go back to the drawing here, think about what that box looks like. If you were to sketch it out in 3 dimensions, 2 meters wide, 3 meters deep, going up 5 meters, and so there's this imaginary box of water. How heavy is it? And the weight of that water is equal to the vertical forces, regardless of whether it's a flat surface like this or the curved surfaces that we're going to get into on Tuesday. So any questions about this hydrostatic forces horizontal plate example? All right. Well, that's all we have for today. Just as a reminder, your homework assignment is due on Tuesday. Be sure to give me something to work with on problem 66. That's not a yes-no problem. That's some explanation, tying it into the fundamentals and so on. Do a calculation proof. All right. Have a great weekend.